Welcome to this video. I am your first author, Ya Hui. In this video, I will introduce a new data mining topic, which is called bump hunting. First, what is bump? Let us consider a social network represented by an undirected graph. In this graph, vertices represent researchers, edges represent collaborations between researchers. Suppose that we are interested in researchers who conduct researches on databases. Then we can divide the vertices into two groups. Green vertices that represent researchers who conduct researches on databases. We refer to these vertices as query nodes. Gray vertices that represent researchers who do not conduct researches on databases. We refer to these vertices as non-query nodes. In other words, query nodes are vertices that we are interested in, and non-query nodes are vertices that we are not interested in. A bump is a connected subgraph that contains as many query nodes as possible and as few non-query nodes as possible. In this social network, since query nodes represent researchers who conduct researches on databases, a bump represents a group of researchers in a database community. Finding such bumps can help us analyze a specific research topic. The problem formulation is as follows. Given an undirected graph G, where V is a set of vertices, E is a set of edges, we refer to a connected subgraph of G as a component of G. Given a set of query nodes Q and a component C of G, we refer to PC as the number of query nodes in C and NC as the number of non-query nodes in C. We define the discrepancy of C as alpha multiplied PC minus NC, where alpha is a regulating weight. It can be seen that a high discrepancy component has a large number of query nodes and a small number of non-query nodes. Given an undirected graph G and a set of query nodes Q, the single bump hunting problem in graphs is to find a component C of G such that the discrepancy of C is maximized. In other words, the objective is to find the maximum discrepancy bump. This discrepancy maximization problem is NP-hard. However, there are often multiple bumps in a zero graph, and hunting the maximum discrepancy bump may not be enough. Thus, different from the previous work, we hunt multiple bumps in a graph. Our problem formulation is as follows. First, given an undirected graph G, where C is a function that maps each edge to a non-negative value that we refer to as edge cost. We refer to CC as the sum of edge costs in a component C of G. Then, given a set of query nodes Q in V, we define the quality of component C as GC minus beta multiplied CC, where GC is a discrepancy of C, and beta is a regulating weight. It can be seen that a high quality component should have a high discrepancy and a small total edge cost. Given an undirected graph G and a set of query nodes Q, the multiple bump hunting problem in graphs is to find the top k non-overlapping components. That is to say, the top k non-overlapping bumps, such that the total quality of these bumps is maximized. This multiple bump hunting problem is NP-hard. We prove that the multiple bump hunting problem can be transformed to a price collecting standard forest problem. In this problem, we consider an undirected graph G, where W is a function that maps each vertex to a non-negative value that we refer to as vertex price. Given a graph G and a target number K, the objective is to find K non-overlapping trees of G, such that the net weight of these trees, that is to say, the sum of vertex price in these trees minus the sum of edge costs in these trees is maximized. In our paper, we hunt multiple bumps by solving the price collecting standard forest problem. The state-of-the-art algorithm for solving this problem is developed by Hedge, etc. There are two phases in the state-of-the-art algorithm, growing and pruning. Growing is to cluster vertices into k non-overlapping trees. Pruning is to extract k non-overlapping subtrays from k non-overlapping trays. For example, given a graph, suppose that k equals 2, and a growing phase cluster vertices in 2 trays. Then, the pruning phase is about extracting 2 non-overlapping subtrays from these 2 trays. Assume that there are 3 subtrays that have positive weights, namely S1, S2, and S3. The weight of S1 is larger than the weight of S2, which is larger than the weight of S3. The state-of-the-art algorithm extracts the maximum weight subtray in each tray. For example, it extracts S1 and S3 as a solution. However, this may not be the best solution. For example, extracting S1 and S2 is better than extracting S1 and S3, since the weight of S2 is larger than the weight of S3. In our paper, we improved the pruning method. We observed that pruning is about solving the price collecting standard forest problem in trays. Given a set of non-overlapping trays, how to extract k non-overlapping subtrays such that the total weight of these subtrays is maximized. We proved that this problem is NP-hard via a reduction from the Boolean 3 satisfiability problem. We propose an approximation algorithm for solving this problem. Our approximation algorithm works in the following way. Given a set of non-overlapping trays, we first push a maximum weight subtray in every tray into a max priority queue, using the weights as priorities. Then, we extract a top subtray in the priority queue. After extracting a top subtray, we find a new maximum weight subtray in the tray that contains the extracted top subtray. We push a new maximum weight subtray into the priority queue. We iteratively extract k non-overlapping subtrays as a solution. For example, given 2 non-overlapping trays in this figure, we first push S1 and S3 into the priority queue, since they are the maximum weight subtrays in the 2 trays. We extract S1. After extracting S1, we find S2 as a new maximum weight subtray in the left tray. We push S2 into the priority queue. If k equals 2, then we extract S1 and S2 as a solution. The solutions of our algorithm are always better than or equal to the solutions of the pruning method of the state-of-the-art algorithm. The approximation guarantee of our algorithm for solving the price collecting standard forest problem in trays is 1 by k. The time complexity is big O kV forest, where V forest is the total number of vertices in an input set of non-overlapping trays. We use our approximation algorithm in trays to improve some existing algorithms. First, we improve the state-of-the-art algorithm for solving the price collecting standard forest problem by replacing the previous pruning method with our new approximation algorithm. Second, there are 3 existing algorithms for hunting a single bump. We incorporate our approximation algorithm into these 3 algorithms for hunting multiple non-overlapping bumps. We conduct experiments using 2 zero datasets, Twitter and DBLP. We use 5 algorithms. First, the state-of-the-art algorithm for solving the price collecting standard forest problem. Second, GBHA, which is our improved state-of-the-art algorithm. Third, 3 adapted bump hunting algorithms. We observe that the state-of-the-art algorithm and our GBHA have similar speeds and are fast. In comparison, the other 3 algorithms are slow. Moreover, the solutions of our GBHA are the best. These experimental results show that our GBHA dominates the existing algorithms for hunting multiple bumps in graphs. After the experiments, we explored 2 applications using 0 datasets. The first application is about finding groups of researchers who conduct research on snake robotics. The second application is about finding regions with high levels of Twitter activity. So this is our work. Thank you for your time.